The rotational review. So the first one, we have basically like a merry-go-round, and you know the mass of the merry-go-round and the radius, and you know where a person is standing. So the merry-go-round is a disk, and the person is a point particle. So in this right here, I am telling you that the moment of inertia of the system is the sum of all the parts. So it's the disk plus the person. So you get the moment of inertia to be 540. You do know that it's rotating at 4 revolutions per second, which is a frequency, and you need it to be in omega. But remember, if you rotate 4 times around per second, then you're doing 8 pi radians per second, because we know that every time you rotate, it's just 2 pi. So all 4 of those rotations times 2 pi gives you 8 pi radians per second. The work done to stop this thing, or the work done to make it go at that rate, is equal to the change in kinetic energy. So you're taking it from rest and giving it 1/2 I omega squared. So the work done is just 1/2 times the moment of inertia times omega squared. And that's where this 170,000 joules comes in. Okay, the second one is the system. So it's got a board, it's got a brick attached to the left, and then the pivot is located right here. Okay, so this whole thing is going to swing down left. So it's going to swing counterclockwise, and there's your pivot. This is the starting position, and then this is the ending position. Okay, so what does it all want to do? It wants to know the initial angular acceleration. Well, angular acceleration is related to torque. So torque equals I alpha. All right, so let's figure out what the torque is. In class, we always decide that if you want to figure out the torques, you should probably think about the forces first. So we have the weight of the brick and then the weight of the board. Now remember, the board, its center mass is just in the center of the board. Torque is a force times a lever arm. So this is the weight of the brick times the distance the brick is away from the pivot, which is 8. The weight of the board times the distance the board is away, the distance the center of the board is away from the pivot. So that's the net torque. The moment of inertia, well, there's really 2 pieces. Number 1, it's the sum of everything. So it's the board plus the brick. Now the board isn't pivoted in the center, it's pivoted off center. So we have to use the parallel axis theorem. So this calculation is saying, well, the parallel axis theorem says that the new moment of inertia is the center mass moment of inertia, 1/12 ml squared and plus md squared, where d in this case is 3. It's how far you move the pivot from the center of mass. So then this right here is the board, this is the brick, and the moment of the system is the board plus the brick. So we have torque equals I alpha, and then we can, if that's the I, then we can find alpha. Okay, now we want to find a velocity of the brick, the maximum velocity of the brick as it swings. So it's going to whoosh down, and we know that the maximum velocity is going to happen when it goes down here. Well, the swing is an energy calculation. So what loses energy? Well, the brick loses energy. How much? Well, mg times its height loss. Well, that's 8, right? The distance this is right here is 8, and it's going to swing all the way down. So that's 8. And in the other one, you can view this in 2 ways, and I didn't do both examples. So see how I have an mg8, and I also have an mg5. But if you really subtract those two, don't you get an mg3? And so really, how much height did the center of the board lose? Well, when it went from here to here, it really only lost a height of 3. But that's what you would get when you did both of those things. So it doesn't matter whether you treat the reference point at 0 or whether you treat it just as the change in height. Remember, potential is all about the change in potential. Effectively, the brick lost 8, and when you put those together, the board lost 3. Okay, and it's that difference that gave the system some rotational energy, right? And we already know the I is here, and so we get a 1/2 I omega squared, and we find omega. But then we know if we know how fast something is spinning, and we know the distance away it is from the pivot, in this case 8, then we can figure out how fast it's moving, right? How fast it's moving is related to how fast it's spinning. Okay. Number 3, a disk is rolling, and since it's rolling, that means it's moving and rotating, and then it goes up to this ramp. So at the beginning, it's moving, 1/2 mv squared, and rolling, 1/2 I omega squared, and v equals omega r. So if we know how fast it was rotating, then we do know how fast it was actually moving. And so we know it's energy. But the energy at the very end is just going to be mgh. So we set the original energy equal to the final energy, and we find the height. And then we say, well, what if it was a hoop? Well, a hoop would actually have a bigger moment of inertia. So this would get bigger, which would make the height get bigger. Okay? All right. All right, this is our yo-yo, but it's a hoop. I think in class I did a disc, and you had to write all 4 equations. So there's the force equation, there's the torque equation, and it looks like I wrote the torque equation. It pivoted in the center. In class, I wrote the torque equation for the center and the edge, and you should be able to do both of those things. The energy is just going to be an mgh and then a 1/2 mv squared and a 1/2 iomega squared, right? It's going to be moving down and then rolling down the string. So probably I use the energy equation to find v. That's probably what I found first, this v. And then I use the v squared equation to find the acceleration. I use the height equation to find time, or I guess I could have just used this to find time. This is me finding the acceleration as a function of g. So this is half g. If remember, a disk was 2/3 g. So a hoop is going to accelerate a little slower down, which makes sense because it's got a bigger moment of inertia. Okay, this is like a for sure problem on the test, right? All right, this is your Atwood machine problem. So this is just the new version of the Atwood machine because now you have a disk that has a moment of inertia. So you have F equals ma here, where mg is winning. You have F equals m here, where the tension is winning. Remember, the tensions are going to be different. The torque on the pulley is the tension 2, which is going to be bigger, versus tension 1, and that equals 1/2 mr squared, alpha, where alpha is a over r. So you got your force equations and your torque equation, and then you got energy. So m2g is going to lose potential, m1g is going to gain it. They're both going to gain kinetic, and the pulley is going to gain rotational energy. So you can solve this thing however you want. I'm not even sure I showed all the algebra. Oh, I did. I solved this for T2 and this for T1, and I put it into the torque equation. And this is me simplifying the torque equation by getting rid of the R's. And then this is me solving for the acceleration. But once you know the acceleration, you can plug back in here to find T2 and then here for T1. And if you want to know alpha, well, it's kind of like V and omega. A equals alpha R, V equals omega R. So once you know either alpha or A, then you can solve for the other one, just like in these ones here. If you knew omega, you knew V. Again, if you knew omega, you knew V. There's always that relationship between V and omega and A and alpha. Okay, this one is difficult, but yeah, we have to be able to do it because it really isn't that crazy. It's just, I know it's a lot of algebra. Now on the test, you are not going to have to do something this abstract, but you should be able to do this particular problem. The problem itself, I don't really think is too bad. It's got conservation of energy, right? This box is going to lose some height. It's going to gain kinetic energy, and the pulley is going to gain rotational energy. It's frictionless, so we don't even have to worry about the work done by heat. There's just a lot of letters in there. The height is d sine theta. Remember, this is the height, so it's the opposite of that. So that's kind of normal for us to say that h equals d sine theta. And then torque's over here, kind of standard. The torque is just tr, 1/2 mr squared, and then a over r for alpha. And then you just do a whole bunch of algebra here. The r's cancel and stuff like that. But I think maybe there's one concept. I did say that the average velocity is the final velocity divided by 2. So that's a helpful thing in doing some of these things. But I think the energy way is the blue, and you get this answer. And then the red is using torques and forces, and you get this. So if you don't like that, and then some of these concepts, that's okay. Don't do them then. Just do the torques and forces. So when you do torques and forces, you get an acceleration. And then if you know the acceleration, you know the time, because you know that the distance it flies down is equal to 1/2 at squared. So just solve that for t, chuck in what you found for the acceleration, and then you get the same answer. And I know it's kind of ugly and it's in the abstract. It's okay. If I gave you numbers on this question, you should be able to do it. And then just take your time if it happens to be in the abstract. Okay, and then this last one is the hardest one, and it is for sure not on the test. Okay, so you don't have to do this one on the test, but this is how a bowling ball actually does roll, down the lane. So the forces in the y hat are just the normal force in gravity. Friction is the only force in the x direction. Friction is causing the torque. So this is torque equals I alpha. Friction, which is mu mg, times r is the torque, and that causes alpha. What you end up having to do is that you solve, right? We talked about this in class. I know it might have only been briefly, but pure rolling, when something is rolling, that means that V equals omega R. So just set those things equal to each other. So if you know alpha and you know A, then really you know these equations. And I know that's like looking back like at the dynamics. We know that V equals V naught minus AT, right? It's going to slow down. And omega equals omega naught plus alpha t. Now in this case, remember, friction is causing a torque. The torque is causing it to spin, and it's gaining spin, and it's losing speed, right? Plus it's gaining alpha, gaining rotation, while it's losing speed, because right away it's not rolling. Okay, so then you can just solve this for V and solve this for omega. So all I'm doing is taking the acceleration and the alpha and plugging them in here. And then I come over here and I do that. I set V right here equal to omega R. And when you do that, you get the time it takes for pure rolling to happen. And then you take that time and you plug it back into here, which is what I'm doing over here. I'm taking this time and I'm chucking it in there, and then I'm finding the exact velocity such that pure rolling happens. And then if you know the velocity that happens, then you can come up here and actually find the distance it takes to get to that velocity. And again, you know everything else. You know the acceleration, so you're solving for x or d. And I know that's a hard one, but this step right here is just you doing forces, right, and finding the acceleration. This step here is you doing torques and finding the alpha. This is using the classic dynamic equations. V equals V naught plus AT, omega equals omega naught plus alpha t, right? They're the same. And then this may be the thing that, got you, is that you weren't really sure what it meant to do pure rolling. But for pure rolling, we're setting V equal to omega R. So do that, set V equal to omega R, solve for time, use time to find the velocity that occurs at. And then if you know the velocity it occurs at, you can use the V squared to find the distance that it actually rolls. Okay, so I do think number 6 is doable. I am not going to put a question like the bowling ball question, though, on the test. Okay, so review all these. This one, concepts are great. You should be able to know it. This was an AP question, maybe like 5 or 6 years ago, but it's not on the test. 5, or this one, for sure, you have to be able to do this one. But I understand the abstract got you, but the concepts are super important, right? It's just energy here. That's energy. And then over here is torques and forces, and you got to be able to do them. Okay? And then, 4 and 5 are for sure questions on the test, right? You're going to have to be able to write me abstract force and torque and energy equations and then solve for a bunch of variables. And these are kind of just smaller questions. But again, this is the work energy theorem, where the work is equal to the change in kinetic energy. We had that on previous tests, except now it's just rotational energy. This one's a good one because the initial kind of action is all about torques and alphas, and then the entire swing is all about energy. And this is like backwards of what we might have done in class. Like in class, we might have rolled something down, but now we're going to roll something up. So it's judging all those things. Hopefully this video kind of helps walk you through the review, but I highly suggest taking a look at the review, the multiple choice, the book work, and getting a good idea of how to be able to write the force, the torque, and the energy equation for all those different situations. And then make sure if you wrote the energy equation, you can solve for velocity, and with velocity you can find acceleration, and with accelerations you can find tensions and times, and these two probably make you do the most, because making you write these abstract equations and then find these things, and abstract equations and then find these things. Again, this stuff here is all kind of like old school review of kinematics, but again, it's important. They pop up in this unit. Okay, so study up, and I'll see you later for the test.